So this is the second of our gas laws. We're looking at Charles's law. He was a Frenchman whose name was Charles, Jacques Charles, and he studied the relationship between temperature and volume of gases, temperature and volume. Now, I realize I'm doing this a little bit out of sequence. The temperature in Charles's law cannot be degrees Celsius, and it cannot be Fahrenheit if you're an American. It can't be any temperature where there's going to be negative values. So we have to use a temperature scale with only positive values, and that's sometimes referred to as an absolute temperature scale. Absolute, like absolute value in math class. Convert any negative number to a positive number by doing absolute value. So the absolute temperature scale. It's sometimes called the Kelvin temperature scale, K-E-L-V-I-N, Kelvin, named after Lord Kelvin, a British scientist, physicist. Kelvin High School is named after the same fellow. So Kelvin temperature scale, there's a lowest possible temperature, and we call that 0 Kelvin. That 0 Kelvin is the lowest temperature. On the Celsius scale, you might want to note for yourself, it's negative 273 degrees Celsius. So 0 Kelvin is negative 273 degrees Celsius. Water freezes at 0 degrees Celsius. On the Kelvin temperature scale, water freezes at positive 273 Kelvin. Water boils at 100 degrees Celsius. On the Kelvin temperature, water would boil at 373 Kelvin. So you can see there's a simple formula. We're going to see this later in the slides, but to get the Kelvin temperature, you simply take the Celsius temperature and you add 273, or technically 273.15. Okay, so the Kelvin temperature equals the Celsius temperature plus 273.15. One little quirk, Celsius is actually referred to as degrees Celsius. We put a degree symbol in front of it. Kelvin, you don't put a degree symbol. You just say Kelvin. So 273 Kelvin is 0 degrees Celsius. All right? So we'll talk a little bit more about that again in just a moment. So the Charles's law is studying the relationship between the absolute temperature, the Kelvin temperatures, and the volume of gases. So in this animation, I can change the temperature of the gas that you see in the middle of the screen in that syringe. I can change the temperature by dragging the little sliding bar to the left or to the right. So here I'm cooling the temperature down for the gas. We'll cool it down to about 149 Kelvin. Now this graph pops up that's just showing us the gas is cooling down. Notice what's happening in the middle of the screen to the plunger. As the gas cools, what's happening to its volume?
Volume decreases.
Yeah, the plunger's dropping, so the volume of gas is decreasing. From yesterday's lesson, what does that mean the relationship will be?
Direct.
Lowering the temperature is lowering the volume. That's right, it's a direct proportion, right? So we could actually skip this animation and just jump to the final analysis, but let's collect the data and we're going to analyze it on our graphing calculators. So write down that temperature, 149. You don't really need to put 0.15. So 149 Kelvin. So create a little table if you haven't already done so. Temperature in Kelvin and volume, and the volume is in cubic centimeters, I think. Milliliters if you prefer. So the first data point is a temperature of 149 Kelvin has a volume of 13 cubic centimeters. So let's create a second data point. I'll warm the gas up. I'm just randomly picking these temperatures. So the second temperature will be 195 Kelvin. 195. And it warmed up, the volume went up to 17.01. 17.0. Why don't we just go to 1 decimal place? Let's warm it up even further. 232 Kelvin. Is 232 Kelvin hot or cold?
Cold.
Remember, 0 degrees Celsius would be 273 Kelvin. So this is what? About 40 degrees below 0-ish, right? So now 232 Kelvin, our volume is 20.2, 20.24 if you want to keep one more digit. Oh, dear God. All right, and then warm it up a bit more. We've just gone above 0 degrees Celsius. We're at 284 Kelvin. And our volume got bigger. It's now 24.8, 24.77 cubic centimeters. And we'll collect maybe 2 more data points. Let's go up to 313 Kelvin. The volume's 27.3 cubic centimeters. And our last data point, let's go up to like 372, which is just like 99 degrees Celsius. So 372 Kelvin, the volume goes up to 32.5, 32.45 milliliters. All right, so now we've got 6 data points. I just double check that you copied everything down correctly. So if you made a mistake, your graph will look bad on your calculator. All right, so I'm going to switch from the PowerPoint to a computer simulation, an emulation of the graphing calculator. Can everybody see the graphing calculator now?
Yep.
All right. So this is emulating the TI-84 plus CE calculator. So on the left side, you see what should look just like the buttons on your calculators. And on the right, in the middle of the screen, is a picture of what you'd see on the screen of the calculator. At the bottom, underneath the screen, you'll be able to see the keystrokes that I'm typing. So let me just clear the keystrokes. So as I type something on the emulation, you'll see the keys underneath, so you can double check if you missed what I did. So we want to enter the data that we just collected. So where do we go on the graphing calculator? What do I press?
Stat.
The stat button?
Yes.
Stat. And then I
Edit.
want to choose number 1, edit. So I just press the number 1 on the keyboard, and that takes me to these lists. If you still have yesterday's data in the lists, then you want to clear that data. So how do we clear the data?
Go to L1, like the top.
Okay, Nathaniel, right now I'm asking rhetorical questions, okay?
Oh, okay.
Okay, I'll try to make it clear when I'm asking a question that I want an answer for. So I put the cursor, the up arrow, and I go up on top of the L1 symbol. If there were any numbers in that list that I'm trying to get rid of, I would now press clear, and then I would press enter to get rid of all the numbers in that list. Go to the right and do the same thing in the second list. Move your cursor up on top of the L2 symbol and say clear and enter to get rid of any numbers in that list. And you could do the same thing for other lists if you like. Okay, so let's go to list 1 and enter your temperatures in list 1. So the first temperature, 149, enter. Second temperature, 195, and just keep going. $284, 313. Using the, I wonder if I could just type these in. 372, yes I can. 372, using my mouse, it's a bit slower. So now go to list 2 and enter your volumes. I'm going to enter the volumes with just 1 decimal place, but you can put 2 if you recorded 2. Notice the first one was 13.0, and I actually typed 13.0, but the calculator just shows 13. 17.0 was the next one. 20.2, 24.8, 27.3, 32.5. Oops.
Hey, Mr. Patnode,
2.5. Yes.
is there an online thing like that that does the same function?
What do you mean an online? You don't have a graphing calculator?
No, I don't.
All right. So you know what you could do possibly is you could, for the purposes of this working at home, I'll post a link on Edmodo where you could download this software that I'm using. It's aimed for teachers, but I think it's going to ask you to put an email address in, and then it'll take you to a 6-month license to have this installed on your computer. Would that work?
Yeah, that would work.
It'll work for home kind of stuff, but if we ever do get back to class, you won't be able to use this in the classroom, of course.
Right.
All right, so there's my temperatures and my volumes. So now I want to create the scatter plot. I want to create a graph of this data. So where do I go on the calculator to create a graph from data? On the top left, if I see the y equals button, if I were to press y equals, that would let me type in a function. So in a math class, you could say y equals 2x squared and graph functions. That's not what I want to do. But I notice when I'm here, I can see right above that, plot 1, plot 2, plot 3. So I bet I could just go up. Yes, I can. I can just go up and I can press enter on any one of those. But the other thing, what you probably should have done, instead of pressing y equals, right above the y equals button on the left, it says the word stat plot. And so if you click second function and then y equals, it takes you to the stat plot menu. So stat, because we're in the stat menu, and plots, we're going to create scatter plot. So right now on my calculator, they're all turned off. If you have one that's already turned on, then I would use that one. It's a little bit faster. Okay, so I'm going to use the first one, which is turned off. So I'll press 1. Please stop me if something's not making sense to you on your own calculator. So because this one was turned off, I have to turn it on. So I'm going to go on the word on and press enter. And now the on is highlighted. Of the types of graphs, the first one is the scatter plot. The second one is a line graph. The third one is a bar graph. And the next ones are like box and whisker plots if you've taken some statistics. So my X list is simply which list should go on the X axis. And for us, we probably want our temperatures on the X axis. Those were the things that I was changing. Those are my independent variables. So my temperatures were in list 1. If they weren't in list 1, I would press second function on the keyboard, and I would go down above the 1, 2, 3, 4, 5, 6. There's L1, L2, L3, up to L6. You could choose which list your X values were in. Same thing with the Y values, the Y list. We wanted volumes, which are in list 2, so I'm good to go. If your Y list doesn't say L2, press second function on your keyboard, and then go down to the 1, 2, 3, 4, 5, 6, and tell it which list had the volumes in it. The mark, that just means what do you want the points to look like on the screen. I like the little squares that are there. And you can change the color if you have a new graphing calculator. So now I want to see the graph. Many people will just press the graph button, and that's not going to work almost always. Why won't that work if you just press graph? It doesn't work because the window settings, you can see on my graph here on the screen, they go from -8 to +8, something like that. But my data is nowhere in that range, so I can't see my graph. So there's two options. You can press the window button at the top of your calculator screen, press window. You can manually set in the window settings. So if I do it manually, my smallest temperature was 149. So if I want, I could say the minimum X value is 140, something like that. My maximum temperature was 372. So maybe I'll go from 140 to 380. I can manually type in my range. If I was going from 140 to 380, the scale that I would use, X scale, if I was doing that by hand, I'd probably go up by 20s or 40s or something like that. I'll say 20. And you could do the same thing for your Y minimum, your Y maximum, and your Y scale. Don't change the resolution and those other things. But what was the faster way to do this instead of manually typing it in?
Automatically something.
We just press the zoom button. So on beside the window button, there's a button that said zoom. And then which of these options do I want?
3.
Number 9.
Number 9, zoom stat. Because we were making a stat plot, zoom stat. Number 9 is where we want to go. So if you press zoom stat, the calculator automatically sets the window settings for you. And now we can see our graph displayed perfectly. If you're curious, press the window button again, and you can see the calculator set the maximum values, okay?
That's a bad note.
In your notes, sketch the graph, and like we did yesterday, as you're sketching it, indicate what the minimum, about 125 Kelvin, what the maximum temperature is, about 400 Kelvin, and then on the y-axis, your volumes, it looks like it starts at about 9 milliliters and goes up to about 36 milliliters. So as you're sketching your graph, make sure you indicate the labels, volume and temperature, and indicate the minimum and maximum value on each axis. And
Bad
then
note.
sketch these 6 points. Yes?
I have a question. So when I press stat plot and I put graph, like after I've put the L1 and everything, it just says error, invalid, dim.
All right, so error invalid dim, what that almost always means is that you're trying to graph something and the list either doesn't contain the data or there's not the same number of values in the lists. So go back to stat plot.
Okay.
How many of the plots are turned on right now?
2.
That's the problem.
Okay.
So the one that you were just using is okay. Go to the second, go to the one that you're not using and turn it off. So the problem was the second plot was trying to create a graph using numbers in a list, and you probably deleted those numbers a few minutes ago.
How do I turn it off again?
So click on that. Which one are you trying to turn off?
Number 2.
So click number 2.
Mm-hmm.
And right now for me, off is highlighted. For you, the word on is highlighted. So just move to the word off and press enter.
I got it. Thank you.
When I pressed zoom, it said zoom 9. It said error syntax.
So error syntax, the word syntax means sort of like confused typing, okay? So usually what that means is that if you press Y equals, try pressing the Y equals button, it's possible somebody has typed in gibberish on one of your equations here. There's something that's trying to graph, but it doesn't make sense. Do you see anything here with text in it?
Yeah. Okay,
So just move down there and clear whatever's there.
Yeah.
And then go press zoom number 9 and see if that works.
It worked.
Okay? So
Thank
syntax error is usually just some weird thing it can't graph. It doesn't understand what you typed. All right, so have we all sketched that graph? Does that match what we said a direct proportion should look like?
Yes.
Yeah.
It's linear. Yeah, that definitely looks like a direct proportion. It sure looks linear. How did we prove yesterday that it was linear? We did that thing called linear
Regression.
Okay, so let's do linear regression now. So press the stat button on your calculator. Stat. Instead of option 1, what does option 1 do again? It lets me enter numbers, right? Edit?
Yep.
I want to do linear regression, so where do I go?
Setup editor.
Nope.
Calc.
I want to go to the right, to the calc menu.
Calc.
Yeah, so move to the right with the arrow. Okay? And now you can see a whole bunch of these things. What do you think the first thing does there? One variable stats. if I imagine you guys wrote a test for me, and imagine I typed in all your test scores in list 1 on my calculator. And
Average.
I could then choose one variable stats, and the calculator would automatically tell me the minimum value, the maximum value, the mean value, the median value. It would tell me all those things about your test scores. That's what one variable stats means. Two variable stats would be sort of like what we're doing here. We have two variables, temperature and volume, and it would give you statistics on the two variables. Median, option 3, is another way of doing a line of best fit. Median. We're doing linear regression, number 4, which is a more common way of doing a line of best fit. What do you think number 5 is? If your graph did not look like a straight line,
Quadratic regression.
but it looked like a parabola, then you would do number 5, which would give you a quadratic regression. It would tell you the quadratic equation that matches the graph. Does that make sense? Cubic regression, if your graph looked like a cubic graph. Quartic regression, if it looks, you get the idea. So these are all going to give you different types of regressions, equations, that match the shape of your graph. Because our graph looked like a straight line, we're using option number 4, linear regression. So choose number 4.
What's number 8?
Oh, don't, Ariel,
Okay.
let's leave that for now, okay? So linear regression, AX plus B. So what does the A mean?
The slope.
Slope. And plus B, that's the
Y
y-intercept,
intercept.
right? So we need to tell it the X list and the Y list. Now I understand some of you don't have the newer calculators, so your screen will just say linreg right now. Just hold on for a moment and I'll review with you what to do next. But for the rest of us, this is pretty straightforward at the beginning. The X list is list 1. The Y list was my volumes in list 2. I honestly don't know what frequency list, but go to store regression equation. Store regression equation. If I want to get the calculator to graph my line for me, I need to store the equation it's going to generate. So we press the vars button. Vars means variables. Okay. Then we go to the right to the y variables. And we choose number 1, functions. And we'll see a list like we saw earlier, y1, y2. You just pick any of them. I'll just pick the first one. So now I'm saying perform linear regression, which means give me the equation of the straight line for the data that's in list 1 and list 2, x's and y's. Take the equation of the line you're going to generate and graph it for me as function y1. That's what this means. And now go to calculate and say enter. So there's the equation of my line. For those of you with the older calculators, are you still waiting there with the screen saying linreg?
Yes.
Okay.
Yep.
So what you want to type now is L1. So second function L1, because that was our X list. Then you put a comma. The comma is right above the number 7 on your keyboard. And then you put L2, which is where our Y values were. Okay. Now, if you were to press enter next, it would give you this equation, but it wouldn't graph it for you. If you'd like to see the graph, put another comma, then press the vars button, V-A-R-S, vars, variables, move to the right to Y variables, choose functions, and then pick Y1 or Y2, whichever one you like. Now your screen should say linreg L1, L2, Y1. Press enter. You should see an equation that looks very much like this. It may not be exactly the same if you typed in your numbers a bit different than I did. Now everybody press graph on the calculator.
Sorry, you said L1, comma L2.
You should have asked me that when I said it. So
Sorry.
your screen should have said linreg
Mhm.
L1, comma L2. Then you were going to press another comma.
Okay.
Then you were going to press the vars button, variables.
Mm-hmm.
Then you went to the right to y variables.
Mm-hmm.
You chose functions.
Yes.
And then you said y1.
Okay.
So now your screen says linreg L1, comma L2, comma y1. Then press enter.
Got it.
Now you should see the equation on your screen.
Mm-hmm.
And if you press graph, you should see this.
Hey, it worked.
Mine
Yes,
says
it does.
error. Syntax. What do I do?
Okay, who am I talking with?
Ella?
Ella. Your calculator says error.
Yeah.
Is there any message beside it?
Syntax.
Syntax. So again, press the y equals button on your calculator. Do you see any other equations typed in that look
Nope.
like nothing else is in there? Did you
No.
see no other equations typed in there?
Nope.
Does your y1 show the equation?
Y1 doesn't have anything in it.
Doesn't have anything in it. Okay, so do you have the older calculator or the newer ones?
The older one.
Walk you through it one more time, okay? So press second function quit. Right above the word mode, it says quit. That takes you back to your main screen, yes?
Yeah.
For everything, clear.
Yes.
So we're gonna walk
Clear.
through this one more time. Press the
Okay.
stat button,
That.
right to the calc menu.
Yeah.
Number 4, linreg.
Yes.
And then on your calculator, you'll type second function and you'll choose L1, which is right above the number, your keypad.
Yes.
Yes?
Yes.
Or you put a comma. The comma is right above the number 7 on your keypad.
Does it look like a U?
The number 7, a button with a comma on it, above the number 7. I don't
I
mean,
did that way wrong.
I don't mean, listen, I don't mean second function. I mean right above the button for number 7, there is another button with a comma on it. Do you see that?
Yeah.
All right. Press the comma and then say L2. So second function L2. Are you good?
Okay.
Put
Yeah,
another
and then
comma. Then press your variables button, vars.
yes.
Go to the right to y variables.
And then
Choose
click the
choose
first one.
functions and choose y1.
Okay.
And then press enter
I did it.
and graph, and you should see the graph showing.
Well, that's
Alright.
cool. Thank you.
You're welcome. All right, so now everybody press the y equals button. See 50,000 significant digits there, right? Which we know are meaningless. So let's just go delete a bunch of these digits. So I'll keep 3 digits maybe, 0.0875, and then I'll just press the delete button on the calculator, DEL, to delete a bunch of these other digits that I don't want. So I'm just cleaning up the equation. Then it says plus and a negative. I'm okay with that, but what could I write instead of plus a negative?
Negative.
Minus.
Minus. So, oops, I just cleared my whole goddamn equation. All right, so I have to do mine again. Stat, calc, linear regression. Let's run this to store equation. Okay. Variables. See why I don't want to post videos like this? Because when I make mistakes, they all show up. Okay. Calculate. So instead of typing plus a negative, I could just type minus, couldn't I? 0.0875. Oh my God. Oh my God, I hate this thing. Wait, I don't even have an undo button. Like, oh my God. Okay, I'm just going to talk you through this now. I'm not going to do that a third time. All right, so on your calculator, you can delete the digits you don't want for both the slope and the y-intercepts, right? Just make it a cleaner looking equation. Okay, do that. And then go to your notes where you sketched your graph, put a line through the data, and write the equation of the line from your calculator. But where the calculator says a y equals, what are we going to write? What's
V
on our
equals-
y-axis? It's volume. So we'll say V equals. And where it says x in the equation, we're going to change the x to the letter.
E.
Oh, we were doing volumes versus what?
Temperature.
Oh, temperature.
Temperature.
T.
That's
So
what it
we'll change the letter x to a capital letter T. Right? Does that make sense to you?
No.
No,
So
I'm confused.
when you graph in math class, it's y on the vertical axis and x on the horizontal axis. That's why the equation says y equals mx plus b. But in our graph, we don't have y on the vertical axis, we have volume. We don't have x on the horizontal axis, we have temperature. Do you agree with that?
Yeah, but we're like,
So when you pressed y equals,
yeah.
you see the equation of your line,
Mm-hmm.
y1 equals. What I'm telling you is in your notes, instead of writing y equals, you'll write v
Oh, okay.
equals. And instead of the letter x in the equation, you'll use the letter T because you have temperature on the x-axis. Okay? And definitely do not include all of those 50,000 significant digits. What was our y-intercept? Was the y-intercept very small?
Yes.
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 Let me just try something here. I deleted my equation by accident. Someone give me, what was the slope of our line?
0.0872.
Okay, so if I just type 0.0872x and I don't put any y-intercept in at all, I'll just pretend it's a 0, and I press graph, hey, look at that. It goes through all my data, doesn't it? So in your notes, don't even include the y-intercept. It's so small that we'll just call it 0. And one reason I want us to do that is because in our notes yesterday, when we talked about the direct proportions, we said they go through the origin, didn't we? The y-intercept was 0. The reason this wasn't exactly 0 is because we were rounding off the numbers and things from the simulation. All right, does that make sense, everybody?
Mm-hmm.
All right, so if this was a direct proportion, I'm gonna switch gears here. Let me go back to Zoom. How do I get out of here? So I'm gonna stop sharing that screen and I'm gonna share my document camera. All right, so in our notes yesterday, we said the equation for a direct proportion. So right now you've sketched this already. You have volume and temperature, and we have this line like this. You wrote your equation, v equals what was it again, 0.0872?
Yeah.
Sorry, instead of x, we have T, capital T for temperature. So that meant V was equal to KT, wasn't it? For direct proportion.
Yes.
So we could divide both sides by T and say V divided by T is constant. And if V divided by T is constant, put a box around that, and put a box around V equals KT. But what can we do if V divided by T is constant? Then V1 over
T1 is equal
has to
to
equal
V2 over T2.
which is usually how Charles's law is written. Charles's law, V1 over T1 equals V2 over T2. All right, so we've now seen in these two simulations an inverse proportion. What did that lead us to yesterday, Boyle's law? It led us to P1 times V1 was equal to P2 times V2. That was an indirect proportion, inverse proportion. Today we saw a direct proportion, and it led us to V1 over T1 equals V2 over T2. Okay? By the way, does it matter whether I write V1 over T1 or T1 over V1? Does it matter?
Yes.
Actually, no. And
Never mind.
think about that
But
for a
if
minute.
now
Think about it for a
it's
minute. Could you take the reciprocal of the left side here? Sure.
Yes.
But then
Yeah.
to be equal, you'd have to take the reciprocal of the
Other
right
side.
side also, and you get T1 over V1 equals T2 over V2. There's nothing wrong with that. It would mean your graph, instead of V versus T, you'd graph T versus V. It would still be a straight line, wouldn't it? The slope would not be the same. The slope would be the reciprocal of this slope. Okay? But this is normally how Charles's law is written. All right, so that's the first two gas laws. Let's look at, we'll look at one more today. So we're going to look at, I'll let you decide what you want to write down here. So can you see the screen yet? I'm not sharing
No.
this yet.
No.
All right, so let me share the screen again. Boom, share the screen and PowerPoint. So you decide if there's anything on this slide that you need to add to your notes. So Jacques Charles, you don't need to know first names. He discovered volume is directly proportional with absolute temperatures. So we're using Kelvin temperatures. So volume is proportional. That little symbol again, that looks like the Greek letter alpha. Volume is proportional to temperature. Or V equals KT. To change the proportion to an equation, you just put a constant in. And that led us to V over T is constant, or V1 over T1 equals V2 over T2. And for this to be true, pressure and the amount of gas have to be held constant. Pressure and moles have to be held constant. Okay? All right. Just a quick note about this absolute temperature scale. If I asked you what temperature is a measurement of, most people would say it measures how hot or how cold things are. That's not the best answer, okay? Temperature is actually a measurement of average kinetic energy of particles. Is there anybody who doesn't know what I mean by kinetic energy? Everybody knows what kinetic energy is? That's awesome.
Can you explain it?
Okay. All
I'm
right.
taking one for the team.
Oh, thank you. Imagine you have a ball sitting at the top of a hill. It's not moving, it's just sitting at the top of the hill. The ball's not moving, so it has zero kinetic energy. Kinetic energy is the energy of anything that's moving, okay? So because the ball's not moving, its kinetic energy is zero. But sitting at the top of the hill, it has a very high potential energy. If somebody were to give that ball just a tiny little nudge, what's going to happen? It's going to roll down to the bottom of the hill. And as it rolls down, it gets faster and faster and faster. So as it's moving faster, what's happening? It's getting more and more kinetic energy. Kinetic energy is the energy of motion. As it moves faster, it has more and more kinetic energy. But where's that kinetic energy coming from? Well, it used to have lots of potential energy at the top of the hill. It's moving to the bottom of the hill where it will have less potential energy. So the potential energy is being converted into kinetic energy. Kinetic energy is the energy of moving objects. When they have more kinetic energy, they move faster. Okay? Temperature is a measurement of the average kinetic energy of the particles. So if your house right now is sitting at, let's say, 20 degrees Celsius inside your house, then all of the gas particles in the air around you, they're all flying around and they're all moving at different speeds, right? They're all flying around at different speeds, but there's an average speed of all the molecules in the air. That means there's an average kinetic energy for the particles. This formula you see on the screen, kinetic energy equals 3/2 RT, is an equation to calculate the average kinetic energy of the particles of gas. The T in that equation is the Kelvin temperature. Make sure you emphasize that it's the Kelvin temperature, the absolute temperature. The letter R is a constant, and we're going to see it again later. It's called the ideal gas constant. The letter R, the ideal gas constant. Its value for this equation would be 8.314. We're going to see it again later. So the value for R in this equation is 8.314. I'll leave out its units for now. The KE is the kinetic energy. Anybody know what the units for energy are?
Joules.
So they're joules, that's right. Capital Joules. Technically, this would be joules per mole. So joules per mole of gas. So when you look at that equation, on the right-hand side, the only variable is the letter T, temperature. 3/2 and R are constants. So that equation is telling you that kinetic energy is directly proportional to temperature. When you double the Kelvin temperature, you've doubled the average kinetic energy of the particles. So kinetic energy, the energy of moving particles, depends only on temperature. Well, what happens when you cool things down? The particles would have less kinetic energy. They would then move more slowly. If you cool it down further, they have less kinetic energy still, and they move even more slowly. Eventually, if you cool the gas down enough, the particles would have so little kinetic energy that they become liquid. The intermolecular forces between the particles would take over, and they would stop being in the gas phase, and now they're in the liquid phase. Do particles in the liquid phase still move around?
Yes.
Yes, they do, but they're not as fast as in the gas phase. If you kept cooling the liquid down, the particles in the liquid would slow down. And eventually, what would happen to the liquid?
Become solid.
It freezes. It's solid. Are the particles in the solid phase still moving?
A bit.
Yes.
Well, they're not moving in the way the gas and liquid particles were moving. They're not moving from point A to point B in the solid, but they're vibrating, they're shaking, they're twisting and turning, but they're not moving anymore from point A to point B, but they're still vibrating and shaking. What if you kept cooling down and you kept cooling down? What's going to happen eventually? The particles
Stop moving.
stop moving. And
Is that zero, Kelvin?
when they stop all motion, then your kinetic energy must now be what? What
Zero.
value? If there's no more motion, the kinetic energy is now 0. Can you have any less movement than stopped? No. So that means you can't have any less energy than 0 energy, right? So when you look up at that equation, if kinetic energy in that equation were 0, what would be the value of T?
Also
0.
T would have to be 0, wouldn't it? So that means there is a lowest possible temperature. And that temperature on the Kelvin scale is 0. And so we call that absolute 0. Okay? What would that temperature be in Celsius?
Negative 273.
Very good. Negative 273 degrees Celsius is absolute 0. Okay? Now at the bottom of the screen, you see that little formula again that we mentioned earlier. The Kelvin temperature is the Celsius plus 273.15. All right. We're gonna
Wait,
wrap-
actually,
yeah.
I have one question or two. So in the kinetic energy equation, Ke is just one value, right?
Yes, that's kinetic energy.
Okay. And my second one is can it get
Measured
infinitely hot?
measured in joules, right?
Yeah.
Okay, say that again.
Can it get infinitely hot?
That's a good question.
Vsauce.
We'll say yes at this point, but at some point the particles in the gas, they turn into what's called a plasma, and eventually even the atomic structure can fall apart. So I don't know that there's any highest temperature, but as you get to super, super, super high temperatures, even the atomic structure starts to break down. Okay?
Nice.
Okay. So the last two laws that we're going to want to know about, there are other combinations, but these two, Avogadro's law, Avogadro was studying moles, the amount of gas, and volume. And then there was Gay-Lussac, another Frenchman. I don't know how they knew he was gay, but that's okay. Gay-Lussac, okay? He was studying temperature and pressure. Now, Avogadro, can you tell me just from your gut feeling, is this going to be an inverse or a direct proportion? The amount of gas and the volume of gas. Are those things directly related or are they inversely related?
Directly.
It's pretty obvious, isn't it? If you put more gas in the balloon, yes, bigger. Right? So volume and moles will end up being directly proportional. So can you sketch what a graph would look like for volume and moles? What would that look like if you graphed volume versus, what's the symbol for moles?
MOL.
No, the symbol for moles is the letter
N.
N, a lowercase n, right? So if you sketch a graph like we just did a minute ago for Charles's law, put volume on the y-axis, put moles on the x-axis, what would that graph look like because it's a direct proportion?
Straight line.
Linear.
It's a linear straight line, just like Charles's law. What would the equation of that line have to be? Instead of V equals KT, this would say V equals K
N.
N. Are you writing that down? V equals Kn. Now rearrange that. What would it say? V divided by N would be constant, wouldn't it? Divided by N is constant, then you could say V1 over N1 equals V2 over N2. Does that make sense? And we can cheat like this because I told you yesterday all of these gas laws are either direct or inverse proportion. Avogadro, when he studied this relationship, nobody told him up front that it would have to be one of these relationships. So he discovered that it was a direct relationship. Now for the last one, Gay-Lussac's law, let's actually do a little simulation, okay? Can you see this video?
Yes.
All right.
Wait,
So this is,
node.
yes.
For the graph, what goes on the x-axis and what goes on the y-axis?
So for Gay-Lussac or for Avogadro?
Avogadro.
Avogadro, it doesn't really matter. You could put either one, but we said V on the y-axis and we said N moles on the x-axis.
Thank you.
Right? But just like Charles's law, it doesn't matter. You could switch them around. If you switch them around, you wouldn't get V1 over N1, you'd get N1 over V1, right?
Yeah, thank you.
You're welcome. All right. I'm trying to play a video. Is this going to work? All right. So can you see this?
Yes.
Yep.
All right, so I'm going to skip ahead. This is a simulation. Let me just describe what they're doing. Beaker. In the beaker, I want to pause the video for me. Okay, in the beaker, they've got alcohol freezing with dry ice. And now, oh, God damn. I'm trying to pause the video because I want you to collect data. They've got a beaker full of alcohol with dry ice, so it's super, super cold. It gets down to almost minus 89 degrees Celsius. They've got a test tube full of gas, air, I think is in this first one, a temperature probe, and a pressure sensor, temperature and pressure. So we're going to be looking at Gay-Lussac's law. And when they put the test tube of air in the super cold alcohol, they're going to start recording temperatures and pressures as it warms up. And if I can, like I did yesterday when I tried this myself, I'm going to be pausing the video so you can actually write down some temperature values and some pressure values. So make a data table for yourself. We can put, it doesn't really matter, but we'll put pressures, let's put temperatures in the first column, and we'll put pressures in the second column. Yeah, this is okay. So temperatures in the first column, pressures in the second column. Notice on the right side, you can see the computer. The temperature in the room is about 22 degrees Celsius, and the pressure in the room is about 101 kPa, so it's very close to standard pressure. But now he's putting the test tube of gas in that super cold alcohol. Look what's going to happen to the temperature and pressure. What's all that bubbling? Anybody?
Carbon dioxide gas.
Boiling.
Yeah, dry, not boiling. Dry ice. What happens to dry ice? It turns directly to gas. It sublimes, right? So what's happening is the dry ice is subliming, turning to carbon dioxide gas, and that gas is bubbling up through the alcohol. So it looks like the alcohol is boiling. It's not. It's super, super cold, right? All right, so I'm going to be pausing the video, and you're going to write down some temperatures and pressures. Here we go. There, you can write down that is your first one. So your temperature is about minus 19.9 degrees Celsius. And the pressure is 88.4 kilopascals. And let's collect some more data. So now the temperature is minus 15.1 degrees Celsius, and the pressure is 90.1 kilopascals. Another one, the temperature is minus 10.5 degrees Celsius, the pressure is 91.6 kPa.
Can you go to the one before this? Sorry.
The last one, the temperature was minus 15.1. The pressure was 90.1.
Okay, thank you.
Okay, there's another one, negative 6.07 or negative 6.1, if you like. And the pressure is now 93.0. And maybe this will be our last data point. So the temperature is now 0.24 and the pressure is 95.1. Let me see if I can get one more in here. We're almost at the end of the video. Okay, we'll do this last one. So the temperature is now 2.9 degrees Celsius and the pressure is 96.0 kilopascals. How are we doing for time? It's 2:20, so we just gone over 1 hour. We can do one of two things. If you've had enough already, you can log off and you can create your own graph on your calculator and see if you can do everything yourself. Or if you want to hang around with me for 5 more minutes, we'll put the data on your calculator together. Okay, so you decide what you want to do. There will be likely a web assignment active tonight, so make sure you check that. And if you have any questions about anything we've been doing so far in this unit, after this lesson at about 2:30-ish, maybe 2:35, since we're going a bit over, I'll be available in a second meeting. I'll have to get the second meeting ID code on Modo, to where you can drop in and ask questions, okay? So if you're going to hang around, let's go to our graphic calculators and enter the data that we just collected. So I'm going to press the Stat button. I'm going to choose option 1, Edit. Can I use lists 3, 4, 5, 6?
Yeah.
Sure. So if I don't want to delete those other numbers, I'll go to list 4. It doesn't really matter as long as you know which list you're using. So negative. Now, do you guys understand on these calculator, at the very bottom on the left side of the enter button, that's your negative symbol. So don't use a minus, use a negative, okay? Minus is the math operation like plus or minus. We want the negative symbol. So negative 19.9. Oh dear God. Ugh, my computer. Negative 19.9. And keep going. Negative 15.1. Look, on my calculator, I was trying to use the keyboard to type negative, and the calculator thinks that's a minus. So I gotta actually push this button. Minus 15.1 and minus 10.5. Oh dear God. Using this emulator is not as nice as it looks. 10.5 minus 6.1. Minus, or 0.24 now. 2.9. Go to the pressures. These will be faster. 88.4. 0.1. 91.6. 93. 95.1. And 96. Anybody still typing numbers in? All right, so now I want to graph this, but remember, we're going to be putting the pressures in the Y list, and we want the temperatures in the X list. But do we have a small problem right now? The temperatures are in Celsius, aren't they? That actually won't matter for the graphing, but let's do something. Are you still with me here? Go to another free list. I'm going to go to L6. You can use any other list you like. Put your cursor up on top of the L symbol. So mine's on top of the L6 symbol. At the bottom of the screen, it should say L6 or L4, whichever list you're using, equals. Yesterday, this is how we did a reciprocal. We said 1 divided by list 2. What I want to do is convert the temperatures, which are in list 4, those are Celsius temperatures. I want to convert them to Kelvin temperatures. So what am I going to type here? List 6 will equal, temperatures
List
are
5
in
plus
list,
273.
very close. The temperatures are actually in list 4 for me.
Oh, sorry.
Unless you're using list 5 for your temperatures. So for me, I've got to go second function L4. So that's where my temperatures were, plus 273.15. And if I press enter, it converts all of the temperatures that were in Celsius to Kelvin temperatures.
I got a error data type.
Okay, did you put your cursor up on top of the L symbol when you did that? Just go back and do it again.
Okay.
So make sure you put the cursor on top of the L symbol.
Oh, okay. I see.
Otherwise, you're telling it to do all this in just one cell, and it can't do that. Did that work?
Yeah.
Okay, so now my temperatures are in list 6. You might be different. My pressures are in list 5. You might be different. I want to make a graph. So I go second function, stat plot. I can use number 1, it's still turned on. My X list is going to be the, what did I say, temperatures. So for me, that's list 6. And my Y list are my pressures, which for me is list 5. And now I'm ready to graph it. What's the fast way to see the graph?
Graph.
Press zoom and option number 9, zoom stat. And look at that. It is a direct proportion, right? Is this something you could have predicted, that it would be a direct proportion?
Yes.
Do you ever see on like a can of spray paint or a can of bug spray or a can of sunscreen, anything that has pressurized gas inside? Did you ever see a warning on the can? Don't throw this in a fire
Yeah.
or explosive or something. Why do they put that warning? Because even when you think the can is empty, it's not. It still has gas in it, but it's just at the same pressure as the gas outside. So therefore, when you press the nozzle, nothing comes out. If you were to throw that in a fire, the temperature will rise, but the can can't get bigger or smaller. It's a rigid can. So what happens to the pressure inside the can if the temperature goes up?
It increases.
Particles move faster, and they hit the walls of their container with more force. And with more force, that creates higher pressure, and the can might blow up.
Boom,
Right?
boom.
Boom, boom. So therefore, raising the temperature made the pressure go higher. And that means it's a direct relationship. Okay? What will the formula look like then?
P over
P will equal KT, which means P1 over T1 will equal P2
over T.
Right? That looks just like Avogadro, and it looks just like Charles's law, because those are all proportions, aren't they? All right, I will stop there. Folks, thank you for tuning in. Take a look for a lesson, an assignment on Webaside. If you have questions, feel free in about 5 minutes or so to log back in to another meeting. The code is on Edmodo. If you have questions, you want to chat, want to get some help on your calculator, you're not sure how to do something, you can help. I can help you sort of one-on-one or in a small group. Yes, Nathaniel.
Oh, it's me, Dan. I'm just wondering, do we have to press turn in again on Edmodo?
If you could just get in the habit of doing that. So for each of these meetings, go press turn in. That way I just get a sense of who was here. Okay?
Okay. Thank you.
Okay.
All right. It's not it's not for any kind of attendance. It's just so that I need to make sure that people are, if there's somebody having problems logging in, I can track them down if they're not able to do that. Okay? Have a great day. Okay?
You.
Thank you.
Bye, Mr. Patnett.